All right, going into polar coordinates, so we're gonna look at a whole new graphing system. So make sure you read through to kind of get an idea of what a polar coordinate represents and how it is drawn. I'm not gonna read the directions to you, but as far as the idea is, we're gonna take those points that are in the rectangular coordinate system and rotate them around a polar coordinate system, which plots an angle with a corresponding radius. All right, example 1, plot the following polar coordinates. So what we want to do here is first make sure we get the angle correct. So a 315 degree angle, again, we start angles in the standard position, out the positive. That's where our angle is 0. And then the terminal ray for 315, we are rotating counterclockwise since it's positive. 270 here, 360 is full, so 315 is somewhere in this region. Here is the angle theta. That is a terrible circle. Let's do it a little bit bigger. The angle theta, 315, and the radius of 2 means we're going out 2 units. So each circle represents a radius of 1 unit. So the inner circle is a radius of 1 unit. We want the second loop. So here is our point right here. Second one, a radius of -2. So when it's negative, we're still going to go out the same. So I'm going to get the angle first. So there's my initial ray, and then the angle pi is here. When the radius is negative, we go the opposite direction of the terminal ray. So because we have a negative radius, I would go out to the right 2 units on R. So the second loop, but opposite the terminal ray. Third one. -1, negative pi half. We always plot our angle first. So initial ray, negative pi half. So now we're rotating clockwise. Negative pi half is here. So here is our angle, negative pi half. And then -1, we're going 1 unit opposite the terminal ray. So the negative angle makes it rotate clockwise, but the negative R still means we go opposite the terminal ray. So we would be here for our point. All right, so there are different ways that you can represent points. So because, again, going back to coterminal angles are technically angles that are in the same position. So we can find a point that is in the exact same spot, just represent it differently. So we've got the point 2 pi thirds. I want you to give me an equivalent point where the radius is positive, but the angle is between 2 pi and 4 pi. So with R being positive, R was given as 2. Remember, it's R comma theta. So we're going to keep R at 2. So I'm going to open my parentheses. My R is going to stay 2. Right now, pi thirds is not in the correct quadrant. So what I want to do is add a rotation until I come up with an angle that is between 0 and 2 pi. So if I add 2 pi, that will put my angle theta in between. So we would take pi thirds and add 2 pi. So an equivalent point would be, let's see, if we multiply by 3 over 3, that would be 7 pi over 3. So this point is in the exact same spot. All right, R less than 0 and our angle between 0 and 2 pi. So R negative, so I was given a radius of 2, so I want to keep it at -2. And remember, when it's plotted negative, it goes out the opposite ray. So what I need to take the given angle and I need to make it go the opposite direction. So instead of adding 2 pi to make it go in a full loop, when you want to change the sign of your radius, you add half a rotation or you add pi. So we would take our given angle pi thirds and we would add pi to it. That would put our angle, so just to kind of give you a visual, our angle of pi thirds is here. If I add pi, the angle now terminates over here. And then because the radius is negative, we would plot on the opposite side. So I would still be plotting the point where pi thirds is. Actually, you know what, we'll just kind of leave that there. It's a rough drawing, but it works. So simplify our point R, -2, comma 4 pi thirds. Then our last one, r greater than 0, so we're holding our radius the same at 2. This time I want a negatively rotated angle, so we're going to take our given angle of pi thirds, and when we want a negatively rotated angle, we're going to subtract 2 pi. So we've got 2 comma negative 5 pi thirds. All right, converting between the two coordinates, so you should be able to take a point in either polar or rectangular form and convert it to the other one. So there's your equations for the relationship. Polar to rectangular, x is r cosine theta and y is r sine theta. All right, so we're given the point negative 5 comma 4 pi thirds. So r is negative 5, theta is 4 pi thirds. So x is equal to r cosine theta. So rx is going to be equal to negative 5 times the cosine of 4 pi thirds. So we're going to simplify. Negative 5 times cosine of 4 pi thirds, straight off your unit circle. That is in quadrant 3, negative 1/2. Multiply together, negative times negative is positive 5/2. So the equivalent x coordinate is 5/2. Y is r sine theta. So negative 5 sine 4 pi thirds. Sine of 4 pi thirds is negative because we're in quadrant 3. Square root of 3/2. So negative times negative is positive 5 square root of 3/2. So our points are written, our coordinates are written as x comma y. So the equivalent point, I'm just going to put a little arrow to show that this is my answer, converted back to rectangular would be 5/2 comma 5 square root of 3/2. So there's our equivalent. All right, next one. Given the polar coordinate radius 4, angle negative 5 pi 6. So x is r cosine theta. So we'll get x converted first. So we've got x equals r 4 cosine theta negative 5 pi 6. So again, that unit circle is just not going away. Negative 5 pi 6, if you're struggling with the visual, get it drawn. Negative 5 pi 6 is rotating this way, but it is coterminal with 7 pi 6, so it's going to be right here. Cosine of 7 pi 6 is negative square root of 3/2. So if positive times negative, negative 4 divided by 2 is 2, 2 square root of 3. For y is equal to r times the sine, r is 4, times the sine of theta, which is negative 5 pi 6. So doing the sine of negative 5 pi 6, still in the same place, 7 pi 6. So sine there, still in quadrant 3, so negative 1/2. And then positive times negative is a negative 2. So the equivalent coordinate, rectangular coordinates, would be negative 2 square root of 3, negative 2. Right. Going the other direction, so there's your rectangular to polar form, r squared equals x squared plus y squared. That will help you with the radius, and then to get the angle, its tangent of theta equals y over x. You just need to be very, very careful. Make sure you put it in the correct quadrant. Okay, we don't want to put it in the wrong quadrant. All right, so first point, convert to rectangular form. So here, convert the rectangular to polar form. So we're given x is negative 1 and y is the square root of 3. So first thing I want to do is find r. So r squared equals x squared plus y squared, so there's no reason to include the square on r. R is always positive, so it's going to be the x value squared plus the y value squared, all under a square root. No worries about plus or minuses when solving for r. So r is 1 squared is, or negative 1 squared is 1. Square root of 3 squared is 3. 1 plus 3 is 4, and the square root of 4 is 2. So our radius is 2. So before we go do the tangent, we need to make sure that we're going to put this angle in the correct quadrant. Okay. So I'm going to go sketch it before I go find it. And I guess we could have drawn the sketch first. So here's my x and y axis. The point negative 1, oh, hang on, negative 1 square root of 3 is negative 1 left and square root of 3 up. So we are here. So if you want to complete your triangle, you can. So here is my x and here is my y. So inverse tangent. Tangent of theta is equal to the ratio of y over x. So square root of 3 over negative 1. Tangent of theta is negative square root of 3. All right, so off of our unit circle, we have tangents. We have angle. We have two angles technically that can be negative square root of 3. If it's helpful, you can think about them in the unsimplified form. So remember, everything around that unit circle all has denominators of 2. So I could rewrite negative square root of 3 as square root of 3 over 2 over 1 over 2 if I wanted to. And as far as the negative, because we're in quadrant 2, is associated with x being negative. So I'm going to negate the x. So if I think about where this point is located, this angle is located, it is where y is the long side and x is the short side but negative. So that is that angle right there. So that means theta equals 2 pi thirds. So our equivalent point in polar form, remember it's r comma theta, our point would be 2, that was the radius, right? Yes, 2 comma 2 pi over 3. Be careful to put it in the correct quadrant, and I think a sketch of your triangle will help that. All right, next one. 2 comma 0. So again, I'll draw it first this time. So x is 2, y is 0. That puts us here. So r equals x squared plus y squared under a square root. So r is 2, because 2 squared is 4, plus 0 squared is still 4, square root of 4 is 2. For our angle, tangent of theta equals y over x. So 0 over 2, which is just 0. So again, there's two places where tangent is 0. Make sure you use the correct angle. So we're going to use the angle 0. Technically, you could use the angle 2 pi and it would also be correct, but I'm going to use the simpler one. I'm going to use 0. So our equivalent, here I'll put theta equals, so theta is 0. So our equivalent point could be 2 comma 0. Or, I'll just put or, 2 comma, because 2 pi is in the same spot. So now we're going to go into polar equations. So converting between equations. So we've converted points back and forth. Now we're going to convert equations back and forth. So we're going to use the same ideas that we have up here at the top to get one equation into the other form. All right, so we've got a rectangular equation. So I know that x plus y equals 3. So what I want to do is translate the x and the y. Since we're trying to go to polar form, I want to translate x and y into what they represent. X is r cosine theta, y is r sine theta. So x, we're going to substitute in r cosine theta, that's the same thing as x, plus r sine theta, that's the same thing as y, equals 3. So goal is when we write a polar equation, we give our polar equations in terms of r equals, so I need to solve for r. So if I look at these two terms, they both have an r in common, so we're going to factor that r out, which is going to give me the factor cosine theta plus sine theta equals 3, and then that r attached with multiplication, so we're going to divide that sum off, so we're going to get r equals 3 divided by the sum of cosine theta plus sine theta. So that is the equivalent polar equation. Let me scooch this down, it's too close. B, x squared plus the quantity y plus 1 squared equals 1. So same thing. We want to sub in our values for x and y. X is r cosine theta, so r cosine theta in place of x, but be careful, it is squared, plus r sine theta plus 1 quantity squared equals 1. So the square on the r cosine can be distributed to the r and the cosine because they're being multiplied together. So that is going to give us r squared times cosine squared theta. However, it cannot be distributed to the one at the back because of the addition of that 1 inside. So instead, think FOIL, we've got to get it multiplied out. So that's going to be, I'm not going to FOIL it out. You should be able to go off to the side and do that if necessary. So r squared sine squared theta plus 2r sine theta plus 1 equals 1. All right. So at this point, we got a whole lot going on. So anytime you see something like this, the pattern is going to be repetitive as to what you do next. I'm looking at these first two terms here, and this cosine squared has an r squared attached to it. This sine squared also has an r squared attached to it. So I'm going to factor it off of those two first. So we're going to get r squared times the quantity cosine squared theta plus sine squared theta. And hopefully that looks familiar. All right, let's go ahead and just drop the rest of this stuff. All right, at this point, like I said, I hope that looks familiar right there. That is Papa Pitt staring you in the face. Identities, again, everything's tying together. Don't forget your identities. Cosine squared of an angle plus sine squared of the same angle is equal to 1. So that is just r squared times 1, which is just r squared. So we're down to r squared plus 2r sine theta plus 1 equals, not 0, equals 1. All right, so goal is to solve for r. So I'm going to get the constant over. I'm going to move the 1 over because when I move it, it's going to 0 out. So we are left with r squared plus 2r times the sine of theta equals 0. So I have two terms, so we want to think factoring. They have an r in common, so we factor that r out, and that leaves us with r plus 2 sine theta equals 0. So set each factor equal to 0. R equals 0 is at the origin. It's pointless, so we don't acknowledge it. It's just a point at the origin. So we can ignore that one. R plus 2 sine theta equals 0. So again, polar equations are written in terms of r, so I would want to solve for r here. I'm running out of room. So we would subtract the 2 sine theta from both sides. So r equals negative 2 sine theta would be our equivalent equation. And here, let me kind of scoochy a little bit, try to get it in a little separation here. There we go. So like I said, the r equals 0 is a single point. It does not need to be included. We can ignore it. So it's just the negative 2 sine theta. All right, going the other way, here's the relationships you're going to need to use. So when we're given the polar equation, going back to rectangular form, we might have to get a little more creative with our algebra. So we're going to use the ideas of r squared is x squared plus y squared. We might have to use r cosine theta equals x, r sine theta equals y, and then we don't forget about that tangent ratio. Tangent of theta is y over x. All right, so now we are going backwards. All right, so the goal here is to get our equations from r and theta to x and y. So different kinds of manipulations. So looking at the equation r equals 4, I don't have a substitution for r, but I have a substitution for r squared. So I'm allowed to square two sides of an equation. So I'm going to square the left side and I am going to square the right side. So what that allows me to do is that gives me the equation r squared equals 16, and then I can use that substitution above, x squared plus y squared equals r squared. So I can sub in that sum x squared plus y squared for the r squared. So I get the rectangular equation x squared plus y squared equals 16, which happens to be the equation of a circle. So that's the equivalent rectangular equation. For B, theta equals 3 pi 4. So once again, if we look at our conversions, we do not have a conversion directly for theta, but as long as I do the same thing to the left and right, I can do what I want. I have a conversion for tangent of theta. So I am going to take tangent of the left side, which means I must also take tangent of the right side of the equation. In doing that, I have tangent of theta equals tangent of 3 pi 4, and tangent of 3 pi 4 straight off the unit circle is -1. Tangent of theta, we now have a conversion for that into rectangular coordinates. Tangent of theta is y over x, so I have y over x equals -1. When we write rectangular coordinates like this, technically you could write it this way. A lot of times we do like to solve for y. It would look just a little bit better so we could recognize it. So you could multiply both sides by x, so we would get the equation y equals -x. And that just helps us recognize what the equation looks like. The last one, we left x and y on the same side because that is the format for a circle. With this one, y over x, we don't really recognize it, but we should be able to recognize the line y equals -x. All right, third one, r equals -2 times secant of theta. So in looking at this, I don't have a conversion for secant. I do have a conversion for cosine. So let's try writing it in terms of cosine. So r equals -2. Secant is the reciprocal of cosine. So I could change this to a fraction with cosine in the denominator. Well, I know I've got a relationship between r and cosine if I could slide those together. So if we multiply both sides by cosine of theta to get it out of that denominator, so cosine theta gets multiplied on the right and cosine theta gets multiplied on the left, a times b, b times a, so r times cosine of theta equals -2. Well, r cosine of theta is the definition of x. So I can now sub in x, so we get the equation x equals -2. So this equation is a vertical line running through x equals -2. And the last one, r equals 10 sine theta. So once again, when we try to plug in, I don't have a conversion for r, but I have a conversion for r squared. So I could square both sides. I could multiply both sides by r. We could do either one. However, in this case, it is a little more helpful to, rather than squaring both sides, substitute in multiply both sides by r, because I have a sign sitting on the opposite side. And if I attach an r to it, I can make a substitution. So I am going to choose, let me just write this equation down. I'm going to multiply both sides by r. So I'm going to multiply the right side by r because I have a conversion for r squared, and that means I have to multiply the other side by r as well. So that's going to give us r squared equals 10 times r sine of theta. Well, r squared is x squared plus y squared, so I can sub that in, x squared plus y squared. R sine theta is y. So I have x squared plus y squared equals 10y. Looking at this, you may not recognize this equation. This equation is hard to recognize. So what you would typically see is everything on the same side here. And then we're going to finagle this a little bit by being creative in completing the square. So this looks like a circle because it's got the x squared and it's got the y squared, but then it's got this random y on the other side. So we're going to go through completing the square to figure out what the equation of this circle is. All right, so I'm going to move my 10y back to the same side as y, and that's going to leave me with an equals 0 on the opposite side. So the x squared, we can leave that alone. We need to manipulate this y squared. So completing the square, it's been a while since you've done that, but the goal is to add something here to force those y terms to factor nicely. Well, if I add something on the left, I have no choice but to also add that number on the right. Recall the formula for completing the square. I'm going to scooch this so I'm not so close to that edge. Is the coefficient of the middle divided by 2 quantity squared. So we're going to take that negative 10, we're going to divide it by 2, and we're going to square it, and that is what we add to both sides to force this thing to factor as a binomial squared. So that gives us x squared plus y squared minus 10y plus negative 5 quantity squared, 25, equals 25. All right, factoring, again, the x squared is just moving on down with everything. We're focusing on the y, so that is going to be a binomial squared, and the binomial is y minus 5. So now we can see that this is also the equation of a circle. The x is squared, the y quantity is also squared. What this means when you have this addition or subtraction in there with one or both of your variables, it's just not centered at the origin. So this circle is actually centered at 0, 5 with a radius of 5. So those are going to be your little more creative ones. And that is the end of the polar introduction.